Hi guys. Okay, hey, we are in the fourth quarter. We are almost done with the year, if you can believe that. So anyway, we're moving on then. So we've got chapter 15 coming up. Chapter 15 is focused on thermodynamics, and thermodynamics is, we'll talk about it more actually, we'll kind of introduce it here, but it is really the reason that like Bartlesville is here. It is all about how do we get energy out of a substance, or how do we determine how much energy. The word itself, thermo, of course, you guys all, I'm sure, associate that with heat, like a thermometer kind of a thing. Dynamic means change. And so really it just breaks down to heat changes. And remember, heat is energy. And so places like Bartlesville that are here because of the petroleum industry, because we have figured out how to get energy out of fossil fuels, is all based on thermodynamics. And so this is a pretty broad introduction. This will be, if you go into engineering, into any kind of chemical engineering in particular, that I'm familiar with, this will be a very in-depth class. So we're going to kind of hit the highlights on this, and there will be some math. Some of it will be kind of familiar to you, but we'll and do some different calculations with some of these. And anyway, hopefully you'll like it. Okay, so here we go. Our first kind of section in this chapter just discusses temperature. So temperature is basically kind of a man-made measurement or thing that is really just our way of saying the how hot or how cold a substance is. And we don't necessarily feel this, but it is proportional to the kinetic energy, the average kinetic energy of the particles within an object. So our probably temperature wise for us, I at least associate that most with air temperature. So today the temperature right now, I think when I checked, was somewhere in the 30s, which is pretty cold to me. In a couple of days, because it's Oklahoma, it'll probably be close to 80, which is pretty hot to me. And so that's, I'm just basing that on temperature, how I feel it. But actually what I'm sensing, like my skin is sensing how fast the air particles are moving. Right, so on a hot day, the particles are moving faster. On a colder day, they are moving slower. Now, they're all still moving super duper fast, but so it's kind of a relative condition. But anyway, so that's what kind of we're thinking about as in terms of temperature. It is very different, well, not very, but it is different than thermal energy. Thermal energy is the sum of all the kinetic energy. So now we're averaging it, we're adding everything up basically of all, excuse me, the particles in an object. And so it depends not only on the temperature, like a hot or cold, or how fast are the particles moving, but also the number of particles, the amount. And so the size of the object comes into play when you're talking about the thermal energy of a substance. And so anyway, so they're related, but not necessarily the same exact thing. Okay, so now temperature in terms of matter. So we, again, like I said, we are very aware of hot or cold because of our sense of touch. But there are some other properties that are based on temperature, and those are called thermometric properties. So this is anything that changes in a predictable way when the temperature changes. So like we know that like a gas expands when it heats up. So like if you've ever left your balloon in a hot car in the summer, when you were a little kid and you did that, and it was super disappointing when you came back and the balloon had burst. That's because you learned the hard way maybe that gases expand as they warm up. Some other things, density changes with the temperature change, and so most substances as they get cooler become more dense. So that's why the solid form of most things will sink in the liquid form of that substance. Ice, water is the one big exception. Remember, water's crazy in terms of all the chemistry that it doesn't follow. But anyway, so there's density. Thermal expansion is another one. So not just gases, but most things will expand somewhat as they get warmer. And so It comes into play in different engineering, structural forms. It's the reason that, like how sidewalks have the little cracks in them. That's for thermal expansion. On a bridge, if you get out on a bridge, if you're walking across it, you might see little gaps in the concrete slabs or in the metal, the kind of the metal construction of the bridge. That's for thermal expansion. So you have that. The thermometer there, we'll talk about it, deals with thermal expansion. Viscosity is another one. Viscosity is defined as an object's resistance to flow. So basically the thickness of the liquid. As you heat an object up, its viscosity gets lower. It becomes more liquidy. It flows easier. And then, of course, the pressure of enclosed gases. So putting the two together, it's not just, okay, I need to wear a jacket today because it's colder. It can also have some pretty big issues in terms of engineering or what substance to choose for this product or those kinds of things. So anyway, again, big deal. Okay. All right, so now temperature scales. Originally, temperature was measured by a thermoscope, which I have a picture of it right there. It was this glass-filled globe. So let me see if I can get something to write on my screen here. So that's the glass-filled globe up there. Gas-filled, sorry. It's attached to a tube. There's actually water in that tube. You can kind of see it down there in that beaker. Down at the bottom, but as the gas expands or contracts, the water level changes. So there weren't any real exact measurements. It's not like it was going to say, 45 degrees, but it did indicate that the temperature was changing, getting warmer or colder. And so it was kind of the beginning. Galileo, I believe, was the person who developed the thermoscope. And so it was the kind of precursor to thermometers. Now, thermometers can take measurements, and they are able to do that because they are based on two known temperatures. So it's a way to calibrate or to kind of mark the thermometer. And those points are called fiduciary points. So just a little bit on that. Initially, fiduciary points were the freezing point of a saltwater solution and the temperature of a person. And that was kind of what people went with. Those ended up not being good, and they weren't that great because the temperature of any solution depends on its concentration. And so if it has a higher concentration of salt, that will influence the temperature, and that kind of thing. And so because everybody might be dealing with slightly different solutions, that didn't work super well in terms of calibration. And then the other fiduciary point initially was the temperature of a person. But if you've ever taken your own temperature, you know that it's not necessarily going to be 98.6. Like we kind of say that's kind of that good temperature for people. But some people have higher or lower just naturally. So again, not great. And so eventually they decided to use pure water, the freezing point and the boiling point of pure water, because everybody had access to pure water. We weren't making a solution out of it or anything like that. And so that's where these temperature scales on the next page kind of ended up. Okay, so here we go. So the temperature scale. So the first one is the one that we are the most familiar with because we're Americans and we are not changing. And that is the Fahrenheit scale. So a man named Daniel Gabriel Fahrenheit in early 1700s, he developed the first accurate thermometer. So a thermometer that was calibrated with marks on it. And he based it on the freezing point of pure water, which he said was 32 degrees Fahrenheit. And then the temperature of a healthy person, 96 degrees. Of course, we've changed that a little bit too. Again, because of the issues with the temperature of a person being changing, he later used the boiling point of pure water as his second fiduciary point at 212. So that's the original. That's one we still use. And then we have Celsius. So Anders Celsius, about 20 years later, developed a scale, and he wanted to have 100 degrees between the fiducial points. So he did use the boiling and freezing point of water. I don't think I necessarily have that written in there. So of water, let's see if I can get my screen to work here. Okay, so water. Okay, maybe not. Oh, seriously, water. There we go. Sorry. Okay, and so he said originally he wanted the zero, the lower temperature, the lower number as the boiling point, and then 100 degrees as the freezing point. And that's kind of what it stayed at. After he died, we switched it to what we know now, 0 degrees is the freezing point and 100 degrees is the boiling point. That one is used in most science labs. That's what most, like our thermometers that we'll use in here, that's a Celsius scale. And it, again, because of the 100 degrees and that kind of thing, it's kind of, I think he was kind of trying to line it up with kind of the base 10 that we associate with the metric system. So anyway, so that's kind of the most common. And then we have the Kelvin scale. So this one is not one that, like, you can't go to Lowe's and buy this thermometer. But about 100 years after Celsius, a man named William Thomson, he was also known as Lord Kelvin, which is why we call it the Kelvin scale. He was Scottish, I believe. Anyway, he developed a temperature scale based on absolute zero. And he said the coldest temperature possible with zero kinetic energy, which, by the way, we haven't fully achieved. And he said that absolute zero is 0 Kelvin. Okay, so no, there's not even like, they don't give him a little degree sign, it's just 0 Kelvin. And then the second fiduciary point is the triple point of water, which is 273 degrees Celsius. And that triple point means that all 3 states of matter can exist as long as the temperature and the pressure are correct. Anyway, and so this one we tend to use with the gas laws, which we talked about in back when we did our chemistry half. And so anyway, so he was kind of the science scale that is used, but kind of variably. Okay, so anyway, this is just a little visual, obviously, to kind of compare the 3 scales. And so it's got kind of the boiling points and those the highest temperature ever recorded in the U.S. 134 degrees Fahrenheit. I'm sure that's somewhere like Arizona. Anyway, Celsius, Kelvin. So notice that these 2 scales are kind of, like here's 100, sort of from 0 to 100, and then they go from 273 to 373. So it's their calibrations are the same. With the Fahrenheit scale, you have bigger degrees, like bigger spaces between the marks. Anyway, and then as you get below 0, so notice the coldest, like the moon down here, is negative 280 degrees Fahrenheit, which is still 100 Kelvin. There's still some movement. And then absolute 0, which, like I said, we haven't figured out how to do that naturally. In space we can get there, but anyway, that's the kind of the comparison. Okay, so just real quick, because we're going to go over these more together in class. These are the formulas to use for temperature conversions. And I know that on your phone you can just do all of this and it just does it for you, but I do want you to see the formulas that we'll use and also be able to use them, which will be some practice on the next couple of pages. So here's a practice. We'll do these together. So either you can do them on your own, which I highly encourage, or look in the book, or we'll do them together in class. Here's another one where we're going to go from Kelvin all the way to Celsius and Fahrenheit. So you'll have to do a couple of different, use a couple of different formulas. Okay, so now on to the second part of this chapter, and it deals more with heat. So and the question is, why do metals warm faster than water? You can just compare any two, but heat. So here is heat. Heat is the movement of thermal energy from an area where there's higher temperatures, so more energy, kinetic energy, to one of lower temperature, lower kinetic energy. Heat, sometimes you'll hear like it's defined as the flow of energy. And so when you put your hand on an object and it feels hot to you or feels warm, what you're really feeling is the thermal energy flowing into your hand. Your hand would have to be cooler for that to happen. If like our table, so when we're in class we'll talk about this, but like when you put your hand on the table, on our black tabletops, it feels cold to you. And that is because your warm hand, its thermal energy is flowing from your hand into the tabletop. And that would continue to go on because you're producing your own heat, or vice versa, depending on hot or cold. Okay, so this transfer of thermal energy. So how does it move? And there are three ways. The first one is conduction, and this is the flow of thermal energy when you have two objects that are in contact with each other. So the energy will flow from the warmer object into the cooler object. Eventually, they will reach like thermal equilibrium, or the temperatures are the same, and energy will stop flowing noticeably. But anyway, so that was pretty common. That's, your hand on the tabletop. That's conduction. Convection is the flow of thermal energy as a fluid. So liquids or gases, remember that's a fluid, as they move. And this is due to the warm particles rising and the colder particles sinking. And so this one, the best example that I always use, and I wish I still had one, but I can't ever get a good one to keep working, is a lava lamp. So if you've ever seen a lava lamp, it's the perfect example of convection. But convection you see that's the reason that our weather does what it does, high pressure, low pressure areas. That's really thermal energy rising, falling. In our oceans, in bodies of water, this happens. You may have you may have noticed something like this, like when you walk out into a pond or a lake, if you can get deep enough, you get to a point where like the top half feels kind of warm, and then like where your feet are down, it's cold. So that's because of convection. Cold stuff sinks. And then finally radiation. So this is the flow of energy in the form of electromagnetic energy. It doesn't require that you move through matter. So like I don't need a solid, liquid, or gas. It's space. And so this one is like how the heat from the sun gets to the earth. And so the rate of this thermal energy movement is kind of depends on the thermal conductivity of the substance, what things are being moved. And some things are good conductors and they help thermal energy move easily, like metal is a good conductor. Other things are thermal insulators and they stop the thermal energy from moving. So like styrofoam is a thermal insulator. It's why coolers are made of styrofoam. Okay, so now measuring this heat. So every substance needs a different amount of thermal energy to change its temperature to get warmer, and this is specifically called the specific heat. And there are tables and charts and all kinds of things about the specific heat of specific types of substances, whether it's pure metal or steel or a piece of wood or whatever it is. And that specific heat is the energy that's needed to raise the temperature of 1 gram of whatever substance by 1 degree Celsius. And so if something has a high specific heat, then you need lots of energy to change the temperature. Water has comparatively a very high specific heat. Low specific heat substances need a lot less energy. Silver, for example, has a very low specific heat. There's a chart in your book, just a very short little condensed version of a specific heat chart. And if you look at the numbers, they're not hugely significant. Like the specific heat of water is 4.18, which is high. And metals like silver are somewhere less than 1. And so that's why, like if you put a piece of metal into your oven, it gets really hot. That's why you have to put on, hot pads to get it out of the oven. Its temperature changes very easily. This formula down here is our other formula for this unit, and it is how to calculate the thermal energy. So how much energy is being transferred when this heat is flowing. And so the Q is equal to thermal energy. That's what it stands for, measured in joules. And then the specific heat typically is a constant, although we'll do some problems where we solve for that constant. M is for the mass, whatever the object is, how big it is. And then T is how many degrees the temperature changes by. So if it goes from 25 degrees up to 40 degrees, then you have then T is 15. So it's just the kind of the change in temperature. Okay, so here's an example of that. We will do this in class, but again, I encourage you to do it on your own. Here's the second one where you're using the same formula, but you're solving for a different variable. We're solving for T. Okay, so now this measuring of specific heat, I hope to do a lab where we get to use calorimetry. And calorimetry is a kind of a lab procedure, I guess, that uses a calorimeter, which we don't have real fancy ones. We can make some out of styrofoam, water, because we know its specific heat, and then a heated object. The calorimeter contains the water. We know the temperature of the water because we can measure it with a thermometer. And then we have this hot object that gets placed into the water. So as you put something hot into water, the water's temperature will rise. The object's temperature will lower until they're equal, so they reach that thermal equilibrium. So then you have temperature that, or you have water that has a new temperature. So I can use that temperature with the formula that we were just looking at to determine the amount of energy that has been transferred, and then use that amount of energy to determine the unknown object's specific heat. It seems like a lot of work to figure out, okay, how much heat would it take to heat this piece of metal up or whatever it is. But knowing that temperature can help in terms of engineering certain things, especially if they're being exposed to high amounts of heat. Will they withstand? Yeah, and then it goes back to, will they expand too much? Will they do all these different things? And so, so anyway, it's a pretty common lab procedure. You know, we have the specific heats for lots of different substances, but it's also can be a way to identify a substance if you don't know what it is. Okay, so here's a picture of a calorimeter, and so you obviously see the water in there. You've got a thermometer, so you're monitoring the water because it's kind of what's taking everything. And then this one's a super fancy one, and so you have this little substance down in this. See where you've got this sample in the cup. So this is whatever we're trying to figure out the specific heat of, and then these ignition wires. Again, this is way fancier than what we would use. So we want to set it on fire. We want to heat it up, see how much it heats up. As it gets hot, the water's going to get hot, and then the temperature is going to rise. And then we can go back and determine, okay, well, if the temperature rose by this much, it means this much heat was produced. And then we can go back and kind of reverse our formula and find the specific heat. Okay. So that's what this example will be about. All right, so then a little bit on heat and changes of state. So changing like from a solid to a liquid. So this graph is called a warming curve. A warming curve. And as you can see, and again, it's kind of, you know this, as you are, if you're anywhere, and we're talking about water here, if you're anywhere below 0 degrees Celsius, water is a solid. It's an ice. It is ice. And as you get to 0 degrees, it will go through the process of melting. So I'm warming it up, and it will melt. And notice that it kind of plateaus right there at 0 degrees. And then it's going to plateau again up here when it's boiling. When you have these phase changes, you see the substance, or excuse me, the temperature kind of level out there for a little bit. That leveling out has to do with the bonds that are holding the molecules together. They are being, loosened in a way, and so the energy is no longer going into the actual particles to help them move faster to become warmer. It is the energy is actually going into those bonds and helping to change or disrupt them. Anyway, and then between 0 and 100, if you have water in those temperature ranges, it is a liquid. And then once you get to 100 degrees, water starts to boil. And again, that boiling, you see that leveling out, has to do with where the energy is being used. So it's no longer being used to make the particles move faster. It's being used to break the intermolecular forces that are holding the molecules themselves together. Notice that it takes a lot less time to melt than it does to boil a substance. It's because it's a much bigger change in terms of the arrangement of the particles. Okay, so this is, as you're going through the video or as you're going through the PowerPoint, this is just a short little video that a college somewhere did, and they're basically just watching ice melt, and they're heating it up. But anyway, what I want you to look at is the temperature change, and they'll kind of update it every so often. But just kind of watch what happens, and what the ice and then liquid are actually doing, and how the temperature is changing or not changing. Okay, so finally, thermodynamics. So the Industrial Revolution happened, as we know, and when we started figuring out how to make simple machines and how to do all this stuff, we realized, excuse me, that heat is kind of a thing. Temperature changes quite a bit. Heat is produced. Thermal energy is being given off in these different ways as it relates to machinery and engines. And so this was a real topic of discussion because, how can we make our engines work better without burning them out? How can we, do this or that? And this is what actually led to the field of thermodynamics. So the study of that thermal energy, heat, how they relate to work, other forms of energy. How can I get something out of this substance that is useful and allows me to do work? So just some early theories on heat before we actually got to the Industrial Revolution full blown. Of course, we had the Greeks who have a thought on everything. They said there were 4 elements: earth, air, wind, and fire. And they never will give it a lot of thought. Actually, they just said, okay, heat and fire are the same thing. And, we went with it. We were like, all right. And then a long time later, 18th century, Joseph Black, who was a Scottish chemist, he said that heat is an invisible self-repelling fluent. So it doesn't like itself, it kind of pushes itself away, that is attracted to other forms of matter, and it has the ability to enter forms of matter, kind of flow in and warm them. And he called this fluid caloric. Okay, so this whole caloric thing, it sounds kind of weird to us, or it does to me at least, because I wasn't there. But this was a pretty prominent theory, and it was pretty good at explaining several things that were being observed at the time. Why do warm objects cool off? Well, because the caloric is pushing itself away. So as the caloric pushes itself away, it takes the heat with it, and the object cools off. Why gases expand as they're heated? Well, as the caloric is attracted to the gas has to kind of make room for the caloric, and so the gas has to spread out. Okay, why the gas laws actually work. And the gas laws, remember, relate temperature, pressure, volume, all those things. So it goes back to expansion. It also was a good explanation for why steam engines work, which was huge at that time, because remember, Industrial Revolution, engines were steam based at that point. And so it was very logical, very reasonable for most of the scientific observations that were going on. And so it was kind of the theory of the day until we kind of stepped away from that, and a man named Benjamin Thompson, who was also known as Count Rumford, he said that heat could be generated through friction. He said heat is not a thing that something has. It's not a substance like caloric. He said that we can produce heat. And so Benjamin Thompson, Count Rumford, he did a lot of things in his lifetime. He's kind of interesting guy. But one of the things he did was he was in charge of basically a cannon factory, like a cannon, shoots cannonballs, used, warfare, all that kind of stuff. And so anyway, to make a cannon, you take a solid cylinder of steel and you drill a hole in it. okay? And when you do that, lots and lots of heat is produced. You have to take a metal drill bit, you have to drill through, and so super duper hot. They used water to keep everything kind of cooled down. And so the caloric theory would say that the heat is caloric being released as the metal is kind of shaved out, as it is bored out. But Count Rumford noticed that the metal would still get hot, even if the drill bit got really dull. No metal shavings were being produced, like nothing was coming out anymore, but still very hot. And so he did all these different experiments where he used, different amounts of water. Like how much water would it take to cool down this cannon as it's being made versus this cannon, and did all these different experiments. And eventually, because of his data, because he, kind of did it the right way, people realized there was way more to heat than just, okay, I open something up and heat comes out. And eventually heat, it was understood, it was realized that heat was related to the movement of the particles, which we now call molecules, and then also the amount of energy those molecules actually had. And so he was kind of the person to say, okay, this caloric theory is not quite working, and kind of the forerunner of the kinetic molecular theory, which is what we do or what we use today. And then just kind of another little guy to throw in there because he's a pretty big deal. James Prescott Joule related heat to mechanical energy. And then he also put some numbers with it and said that a calorie, which he called a unit of heat, or unit of energy, sorry, so a calorie of mechanical energy is equal to 4.18 joules. And so anyway, so he was kind of the energy guy in all of that. Okay, so we've wrapped kind of up on thermodynamics. One more thing though. So now thermodynamics is not really new to us because we've been actually kind of looking at least the first law for quite some time. And so just kind of to wrap it up, these last three, or this last slide, I've got the 3 laws of thermodynamics, just so you see them. They're here. We're living our life kind of based on these, particularly the first 2. So the first law of thermodynamics, we have been correctly also using this same law and calling it the law of conservation of energy. Same thing. But anyways, the first law says energy cannot be created or destroyed, but only transformed into other forms of energy. Okay, totally true. The second law of thermodynamics is not one that we've really talked about, but we know it. And this one says during spontaneous reactions, the entropy, which means disorder in the universe, increases. So when things just happen, entropy or disorder tends to increase. Things kind of naturally, if we're going to kind of keep order, we have to keep putting energy back into a substance, into a situation, into, whatever it is. I always use the example of like my desk here at the front of the room. My desk, particularly as the day or as the week goes on, increases in disorder significantly. Like if I try and kind of straighten it up at least before I leave on Friday afternoon. But Monday morning, as soon as I get here, what do? I start messing papers up, changing stacks around, throwing things up here. And that's kind of spontaneous. I'm not trying anything. I'm not, it's just happening. You might see this in your room, your bedroom at home. Your mom might, in her well-meaning way, ask you to clean your room at some point, and you stop and you put some energy into it, and you pick up all the dirty clothes, you make the bed, whatever, you take dirty dishes to the kitchen. That's not spontaneous. You're having to put energy into it. But then as, the week goes on, you stop putting energy into it and you just live your life, and the disorder increases. Nature does the same thing. And so that's the second law. The third law is one that is, I should have looked one up before I started this video, but it basically says the entropy of a system, the disorder in a system, becomes constant. So it kind of levels out as the temperature approaches absolute zero. Like you can't get any more disordered, basically, is what they're saying here. And so that one's a little, for us, is kind of out there. The first two, though, for sure are super duper important in terms of kind of what we experience, even if we're not aware of it. So anyway, this is thermo. Big introduction. There's much more to it that you will see a little bit more when we do this in chemistry in a couple of years, but definitely if you go on and decide to study some kind of engineering in college. Whew, okay. Bye, guys.